Good morning, Andres. The floor is yours.
Good morning. Thank you. Okay, what I will be talking about today is how data collection, analytics, and modeling could be put to use with an intent towards creating good cities. Throughout the last couple of decades, we can observe two parallel movements in urbanism that haven't had all that much crossover. On the one hand, there's been a veritable trend amongst mayors, amongst urbanists, amongst theorists to think of a 21st century humane city, perhaps most famously advocated by folks like Jan Gehl or William White. This vision of a future is entirely human-centered and focuses on quality of life and quality of environments in cities. On the other hand, there's been a smart cities movement that is mostly focused on technology, on how sensing, Internet of Things, and analytics can transform some of the urban functions and operations. Here on the screen, you see a concept design for an intersection for an automated vehicle traffic. And those two trends stand at odds because much of the smart cities work has lacked a vision of what kind of a city do these technologies add up to. If you think about being a driver on this intersection on the right, it may be efficient. If you think about being a pedestrian on this intersection, it's probably the worst one you've ever encountered. So what I'm trying to focus on today are examples of work where urban analytics is put to use to directly feed into and advocate for city design that urban designers, architects, and planners may support. There's another example of these two kind of parallel trends in application. On the left, you see the recently much publicized work of Anne Hidalgo and her team in Paris, transforming streets and public spaces increasingly into pedestrian, cycle-friendly, family-friendly environments. And on the right, you see a sort of smart cities type of application of congestion charging in Singapore, which ensures that traffic flows and everybody who drives into the city center pays a fee, but has an unintended side consequence of rendering the city increasingly more auto-oriented as a result. So how can we use urban data analytics to support good city design? I will give two concrete examples of some of our recent work. The first talks about pedestrian impact assessments as opposed to traffic impact assessments. Most cities in the developed or industrialized parts of the world require developers to implement environmental review before they get their permits to build. And as part of environmental review, there's oftentimes traffic impact assessments. Traffic impact assessments essentially analyze how a proposed project is likely going to affect traffic flow, vehicular traffic flow on streets around it. Normally, this is performed for peak periods like the morning or evening peak period. And the work centers on how many additional vehicles these projects are going to put on the roadways and whether or not the level of service or capacity of the roadways can handle that. And if it cannot, then by law, it is legally required in many countries and in many cities that developers contribute to mitigation efforts. This oftentimes results in signal readjustments, road widening, parking provisions, or addition of turning lanes. It's a hidden policy mechanism that project by project transforms cities to accommodate smoother vehicle flow around the global north. And what I'm going to talk about is, can we do something like that instead for pedestrians? This study I'm going to talk about focuses on Melbourne, Australia, oftentimes ranked one of the more livable cities in the world by various indices like The Economist or Mercer, etc., if you can afford to live there. Melbourne is one of those cities where it's essentially a CBD type of city where you have close to 3 million jobs, but only 500,000 residents. So there's a whole lot of people who commute in by trains and cars to the city center and then out to the suburbs later. So in this study, we used pedestrian counter sensors that the city of Melbourne has operated for close to 15 years. These are infrared anonymous sensors, oftentimes posted above sidewalks, as you see on the left on this cantilevering post. And they have been counting pedestrians instead of traffic for at 1 hour intervals 24/7. On the left, on the right, you see a sort of on the top chart, a plot of daily activity averaged across all sensors. There's currently around 90 of them on downtown streets in Melbourne. This 3-hump purple line represents the sort of typical daily pattern of pedestrians. There's a morning peak, there's a lunch peak, and there's an evening peak. And the gray line underneath is an weekend trend, which is far smoother, and you can sort of see how people make their way into the city by just around 2 p.m. And on the bottom, you can see how the trend is almost identical on wet, rainy days and dry days, except there's just a shift downward in total activity. So in this study, what we did is we collected data on multiple years longitudinally from all the sensors that were available in the city center, which are marked by these orange dots. These sensors are on all sorts of various streets, ranging from main streets to riverfronts to back lanes to more neighborhood main streets. We put this data from pedestrian count sensors together with data from what's called the Census of Land Use and Employment, or CLUE data. It's an address level data set that describes how many residents, jobs, gross floor areas, and even restaurant seats or establishments are found at every address in the city. And we additionally factored in weather conditions that were available from historic databases of weather in Melbourne. When we put this data in geospatial maps, it constitutes a whole range of address points with all sorts of properties at every address point. And the city of Melbourne has been one of the few cities in the whole world that has maintained a high quality pedestrian infrastructure network data set. So these walkways that you see underneath, these lines, they represent pedestrian infrastructure, not road center lines. They represent sidewalks, crosswalks, overpasses, and they actually even go all the way to the building lobbies, which we didn't include in this case. So what we do with all this data is that we model trips between the very likely origins and destinations during different times of the day. So for instance, in the morning, you may have trips starting from train stations as people arrive in the city center and going to the offices. We model as they might flow over the street network along likely routes by factoring in what we know about pedestrian behavior. And this constitutes a sort of origin destination matrix of trips. We have 56 possible trip types here, and we narrow this down to around 10 or a dozen most important or dominant trips for each period, the morning period, the lunch period, the evening period. And then what we do with this is we fit these predictive or explanatory models to the actual data. The fact that Melbourne has been collecting this data for over 10 years is important in two specific ways. On the one hand, the availability of pedestrian data that is collected at hourly intervals across many sensors gives us an ability to average it out for a typical Monday or a typical Tuesday or a typical weekend day, which is usually very hard to do because in-person collection on the ground is very labor intensive and it requires people to spend their time. So with these sensors, we can have more reliable data sets to calibrate models on. And second, because the data is longitudinal over multiple years, we can build a forecasting model about how pedestrian behavior or pedestrian activities might change over time, and then check using next year's records how good our model was. This is what you see in this chart here. On the top, you see a calibration table, which describes how well our model fits to data from June 2014. So what we did is we modeled hypothetical walking trips from various buildings to other buildings in the city center, and we fit it against the observed data from the sensors. And these are different types of models we fitted. The first one is multi-level model, and then the remainder are machine learning types of models like standard vector regression, random forest, bagging, and so forth. We ended up choosing the standard vector regression model that fit the best and dealt with some of the underlying data issues the best. And you can see that it fits about 92% during the morning peak hour, which is from 8 a.m. to 9 a.m., 96% during the lunch period, and 93% during the evening peak period between 5 and 6 p.m. Now, once it's calibrated, we can use this model to predict how pedestrian foot traffic might change in the following year as a result of new developments in the city center. So we take this calibrated model and we add in all the developments that we know happened in the year after: new buildings, new distributions of residences or jobs in the city center, new restaurants, and so forth. And by adding these new land uses in, we forecast how they are likely going to change foot traffic in the following year. And that's what we see on the bottom chart. These are model fits to predicted data. So it's out of sample, it's not being calibrated on these. These are actual predictions the year after. And as expected, the model fit would decrease to some extent to 78% for lunch period, 82%, for AM period, 82% for lunch, and 74% for PM period, but it's still a fairly robust model. It tells us we can relatively accurately forecast how pedestrian traffic in the city center changes year on year as a result of development activity that takes place. We can also break this down to feature importance to understand what particular types of flows explain the foot traffic at different times of the day. So during the AM peak period on the top left, you see that foot traffic is really dominated by walks from employment, between train stations and employment locations. So this is walks from trains to jobs, followed by walks from car park lots to jobs, followed by walks from homes to jobs and so forth, and some other things like people going to parks and running and taking out their dogs and so forth. During lunch, foot traffic is really dominated by pedestrian traffic from amenities to amenities. This is people walking from shops to other shops, running errands, conducting their daily business outside of work. And in the evening period on the bottom left, the pattern reverts back to quite similar to what's happening in the morning, with some more diverse activities going, for instance, including trips like from jobs to food and beverage places. That is also factored in as a significant effect. But it's dominated again by people going back to train stations and taking the trains back. So these sorts of models help us break down, also understand what kinds of journeys are happening in different neighborhoods of the city. Now, if we spatialize that, then even though the model is calibrated only on a handful of locations, around 60 sensors, which are marked in yellow, orange in this case, after it's calibrated, we can use the calibrated model to forecast or explain foot traffic on virtually every street in the city center. So that's the power of fitting these models, that we don't actually need a sensor every street. We just need a representative sample of sensors that allows us to calibrate a good enough model to then forecast foot traffic on every street. And we can also look at how developments that happened from one year to another might change foot traffic. So on this map here, you see in the building footprints, what is marked in red are decreases in either jobs or residents, and in blue or light blue, these are increases in jobs and residents, and the gray ones represent new developments altogether. And then on the streets, we show forecasted reduction or diminishing of, red shows diminishing pedestrian traffic, and blue shows increasing pedestrian traffic. So what's the purpose of all this? What we hope that can be done with this is, just like we do vehicular impact assessments as part of development review, you can imagine how we can take this to do pedestrian impact assessments. What I showed you was a citywide analysis, including all projects and developments that happened between 2014 and 15. But this can be done also project by project. And once you have a calibrated model, you can forecast how an individual development is likely going to change foot traffic during different times of the day, and thereby solicit developer contributions, not to mitigate how vehicular traffic ought to be improved, but rather how pedestrian traffic should be improved. So get developers to help contribute to city budgets to improve crosswalks, make safe crossings, to have better sidewalks, better public spaces, and so forth. And I think that this change in the mindset from what we currently have in almost every city of the world, from doing traffic impact assessments to pedestrian impact assessments, could go a long way as a sort of hidden but important policy mechanism to make sure that cities, one building at a time, make environments more walkable and safe for non-motorized users. Now, the second project or analysis I want to show involves understanding pedestrian behavior on city streets. Oftentimes, pedestrians are faced with route choice, how to walk from A to B. There's many routes available. As an example here, I've picked Manhattan, which has a famous grid, and the origin point is St. Patrick's Cathedral, and destination is Carnegie Hall. There's 84 different routes that are exactly the same length between them because of the nature of the grid. And how people choose to walk can illustrate what particular street qualities are attractive to pedestrians. These street qualities can be very many. They can involve vegetation, ground floor businesses, the quality of the surface, the width of the sidewalk, and so on. So in this analysis, we used data sourced from an activity-based app in 2 cities in the United States. These are anonymized GPS traces of app users who walked in cities. This data was also collected from 2014 to 15. One data set that we've cleaned and prepared for Boston covers most of the city with around 11,000 traces, and the other one is for San Francisco with about 14,000 GPS traces. Now, once we know the actual routes that somebody anonymously walked, we can extract the origin and the destination of that walk and match it to the actual street network that describes the built environment in that city. So this is called map matching. And once we've done that, we can construct alternatives that the person may have walked, which are roughly similar distance, but they didn't. So this is called alternative generation in route choice modeling. And what this allows us to do is to statistically analyze what is it about the routes that people actually chose that made them preferable, if we analyze the sort of properties of the alternative, unused routes, and the actual route. What we find here is the following. Generally, people always, or not always, but one of the most important factors for route choice is distance. People generally minimize distance. They don't take routes that are excessively long, but they are willing to deviate over the shortest route to access more interesting or useful or safe street properties. So for instance, in San Francisco, we see that people usually try to avoid turns on their routes. They choose routes that involve fewer turns, and we can convert the model coefficients that we achieve to what are called willingness to walk or distance equivalents in meters. So for instance, one turn in San Francisco is roughly felt or perceived as equivalent to walking 62 additional meters. In Boston, that effect is about 34 meters. However, if you have ground floor amenities like shops, services, restaurants facing sidewalks, those are actually perceived as positive. So if a route involves, let's say, 10 extra amenities, then in San Francisco, an average pedestrian is willing to walk an extra 18 meters to experience such a sidewalk. And in Boston, the effect is roughly half of that, and so on. So we can use these types of route choice models to statistically analyze how properties of streets and sidewalks attract people to them. And in fact, something similar has been done for bicycles by another study by Hood and their colleagues. And the ultimate use case of where this can become quite useful is that we can start mapping catchment areas or accessibilities to certain types of destinations in cities, not according to objective distance, not as a 10-minute walk shed or 20-minute walk shed, but rather as perceived distances. And I'm going to try to give you an example of that using a live website share from a different source. So this website called boston.transitaccess.com is one that shows how this plays out. If I can close this at the same time. So when we look at particular stations, what I've put up here is the red buffer represents the half a mile objective walkshed. This is exactly, if you follow the streets half a mile from a transit stations. This map is actually around commuter rail stations. These are basically heavy rail urban transit stations. So the red buffer represents the half mile objective walkshed, but the yellow overlay on top of it represents perceived half miles or perceived 10-minute walks around stations. And these are generally smaller because of the negative street qualities, like having noisy roads or lack of amenities or lack of greenery or narrow sidewalks. And the difference can be very substantial in some instances. You can have, half or even more larger walksheds in some of the cases than others. And we did something similar for also bicycles. So we can turn on the bicycle network and the bicycle perceived distances, then the sort of larger green underlay is the objective 1.5 mile bike radius, and the light green is the perceived 1.5 bike range. And if we look at some of the summary statistics here, we see that, for instance, for pedestrian access, how we evaluate, how we analyze catchments for transit stations has a huge implications on what we find. If we use circular walksheds, which are as a crow flies distance, then compared to those across all 140 stations in Greater Boston, we find that these perceived 10-minute walksheds actually capture only 23% of the population. If we look at employment, only 38% of the population is that would be otherwise included in a circular buffer is found in the perceived 10-minute walksheds. So this has direct implications for planning transit, and in particular, it helps us delineate more realistic and likely geographic extents of who benefits from transit investments and where can we do transit-oriented development so that people would actually walk to transit stations and use that to get around, which is obviously a very important target goal for city governments. So with that, I will stop there, and I'm not sure if we go straight to the next presentation or happy to also engage in some questions.
Thank you, Andres. Fascinating stuff. We are few minutes behind schedule, so we will take the Q&As with you later on in the panel. I don't see that there's been too many questions yet, so probably the viewers are digesting all the cool data analytics that you showed. I was just wondering, maybe quickly, you're in MIT and you're doing research in Melbourne. So is it difficult to do that through? Are you also there in Melbourne sometimes, or do you do it all remotely?
No, this work has been largely done remotely, but Melbourne has been attractive because it's a city that collects good data, and in particular good data for pedestrians. Very few cities in the world do that. Very few cities have official pedestrian counters of that magnitude in place and publicize the data through open APIs. And so these days, we do research globally around many parts.
Okay, thank you, Andres.